Section 7.1. In this section, we are going to learn how to verify the fundamental trigonometric identities and simplifying the trigonometric functions. We have to use the identities that we've learned from chapters 5 and 6 from Math 186 class, and I'm listing them here so that you have something to refer back to. Example 1. Verify tangent of theta times cosine of theta equals sine of theta. Verifying means that you have to prove that tangent of theta times cosine of theta equals sine of theta. So in this statement, they told you that tangent of theta times cosine of theta equals sine of theta. But you have to assume that you don't know this, and you are trying to show them that they are actually equals to each other. So what I'm going to do is, using my equal sign as the boundary, I divide it into two halves, and I have the left hand side and the right hand side. Now I'm assuming that I don't know tangent of theta times cosine of theta equals sine of theta. I would choose one side and trying to show that it's actually equal to the other side. For example, if I choose the left hand side, then I have to ignore the right hand side. I will use whatever I have on the left hand side, tangent of theta times cosine of theta, and try to rewrite it so it looks like the right hand side. Most of the time, I would choose the side that looks more complicated, because when they look more complicated, they have more information for you to work on. So I'm going to go ahead and pick the left hand side. My left hand side is tangent of theta times cosine of theta. I am ignoring my right hand side for now. I'm just assuming that I don't have this, and I'm trying to rewrite this so it will end up being sine of theta. So in here, I'm looking into these two trig functions. I noticed that I can rewrite tangent of theta into sine of theta over cosine of theta. And from here, cosine of theta is canceling each other out, and I end up with sine of theta. So I have just shown you that if you have tangent of theta times cosine of theta, is actually equal to sine of theta, which means I have verified this identity. The process is, I chose the left hand side and I use whatever I have on the left hand side to work my way until I get the function on the right hand side. That means this statement is verified. Example 2. Verifying the following equivalency using the even-odd identities. So in this example, they even tell you to use a certain identity, which is in this case the even or odd identity. So if you go back to the identity page, this is the even-odd identity. I have 6 different trig functions. There are only 2 of them are even, which are cosine and secant. Cosine is even, so that when I take cosine of negative theta, it will be equal to cosine of theta. Secant is even, so when I take secant of negative theta, it becomes secant of theta. So for even function, it does not matter what your input is, whether if it's negative or positive, you get the same outcome. Tangent, cotangent, sine, and cosecant are odd functions. Tangent of negative theta equals negative of tangent theta. Cotangent of negative theta equals negative cotangent theta. Sine of negative theta equals negative sine of theta. Cosecant of negative theta equals negative cosecant of theta. Tangent, cotangent, sine, and cosecant are arc functions. So when I substitute the input with the negative theta, the outcome is going to be the negative of the function of the theta. Going back to the example here, I use my equal sign as a boundary. I have left-hand side and right-hand side. I am going to start with my left-hand side because it looks more complicated. It looks like I can have more information from using the left-hand side. I have 1 plus sine times 1 plus sine of negative x. Sine of negative x can be simplified by using the even odd identities. Sine is an arc function, so sine of negative x is equivalent to the negative sine of x. Next, I am going to multiply it out. I take 1 times 1 equals 1. 1 times negative sine x is negative sine x. Sine x times 1 is sine x. Sine x times negative sine x is negative sine x squared. From here, I have negative sine x and positive sine x. These two will cancel each other out. I end up with 1 minus sine squared x. At this point, my right-hand side is cosine squared x. My left-hand side is 1 minus sine squared x. They don't look alike yet. Going back to my identity page, under Pythagorean Identities, I have cosine squared theta plus sine squared theta equals 1. So I am going to use this identity here. The Pythagorean identity says cosine squared x plus sine squared x equals 1. Now imagine if I subtract sine squared x from both sides. I subtract sine squared x from here and subtract sine squared x from here. Then I end up with cosine squared x equals 1 minus sine squared x. This is just another variation of this. These two are equivalent. So from here, I have 1 minus sine squared x, which actually can be replaced with cosine squared x by using the Pythagorean identity. So from here, I have my right-hand side from 1 plus sine x times 1 plus sine of negative x. I rewrote it to cosine squared x, which looks like my right-hand side. So that means this statement is being verified. Example 3. Verifying the identity secant squared theta minus 1 over secant squared theta equals sine squared theta. My left-hand side is secant squared theta minus 1 over secant squared theta. My right-hand side is sine squared theta. I will choose my left-hand side to start with. Now, assuming that I don't know anything about the right-hand side, so assuming that I don't know this is actually equal to sine squared theta, I am trying to make it look like sine squared theta. So this is all I have for now. I don't have the other side to work with. I only have this side. So secant squared theta minus 1. If you go back to the identity page, under the Pythagorean identity, we have 1 plus tangent squared theta equals secant squared theta. This is the identity that I am going to use. Now, if I subtract 1 from both sides of this identity, I have tangent squared theta equals secant squared theta minus 1. This is still the Pythagorean identity. This is just another variation of this. So from here, I can totally replace secant squared theta minus 1 with tangent squared theta. From here, I will try to turn tangent squared theta into something with sine and cosine, and secant squared theta into something with sine and cosine. The reason why I'm doing this because I want to have sine, right? I want it to look like the right-hand side, and the right-hand side is only having sine squared theta. So tangent is sine over cosine. Tangent squared theta is sine squared theta over cosine squared theta. Secant is 1 over cosine. So secant squared theta is 1 over cosine squared theta. I have a complex fraction here. I have a fraction over another fraction, which means the top fraction is divided by the bottom fraction. So I'm going to rewrite this fraction bar into a division symbol. In order to divide two fractions, I'll take the first fraction multiplied by the reciprocal of the second fraction. And from here, cosine squared theta is canceling each other out, and I end up with sine squared theta over 1, which is sine squared theta. And I have verified this identity by showing my audience that I started with the left-hand side and I rewrote it, and it ended up to be equal to my right-hand side. Example 4. Create an identity for the expression 2 tangent theta times secant theta by writing strictly in terms of sine. In this example, they don't want you to verify it. They're not giving you a statement. They only gave you an expression, and they want you to create an identity, which means they're asking you 2 tangent theta times secant theta equals what? You need to fill in this blank. And in this blank right here, they only want it in terms of sine, which means no secant, no cosecant, no cotangent, no cosine. It's only in terms of sine. Okay, so I will fill in this blank, and in this blank, I only allow to have sine, not any other trig functions. I will start with 2 tangent theta times secant theta. And I will try to rewrite tangent in terms of sine and cosine, secant also in terms of sine and cosine. Tangent of theta is sine of theta over cosine of theta. Secant of theta is 1 over cosine of theta. I'm not done yet because in this, there is cosine, and I'm not allowed to have cosine. So I'm trying to find a way to replace cosine with sine. So what I'm going to do is going to multiply them across. I'll take 2 times sine times 1 is 2 sine theta over cosine theta times cosine theta, which is cosine squared of theta. I'm still not done yet because there's still cosine in here. So in order to replace this cosine squared of theta into something in terms of sine, I'm using the Pythagorean identity. Remember that we have cosine square of theta plus sine square of theta equals 1. So cosine square of theta is actually equivalent to 1 minus sine square of theta. So I'm going to replace the cosine square of theta. Cosine square of theta is replaced with 1 minus sine square of theta by using the Pythagorean identity. And this is my answer in terms of sine only. Example 5. Simplifying by rewriting and using the identities. I have cosecant squared theta minus cotangent squared theta. I want to simplify this. Cosecant square, cotangent square. I think I can use the Pythagorean identity. So let's go back to the identity page. I have 1 plus cotangent squared theta equals cosecant squared theta. So I'm going to use this one. From the Pythagorean identity, I know that cosecant squared theta equals 1 plus cotangent squared theta. I am going to replace this cosecant squared theta with 1 plus cotangent squared theta. And cotangent squared theta minus cotangent squared theta is 0. I end up with 1. So this expression, cosecant squared theta minus cotangent squared theta equals 1. Example 6. Filling the blanks. I have 3 questions. A. If cotangent x is negative 2, then cotangent of negative x equals. In this example, I have to use even odd identities. Cotangent is an odd function, so cotangent of negative x equals negative of cotangent x. So whatever cotangent x is, cotangent of negative x is the negative of it. Cotangent x is the negative 2. Cotangent of negative x is negative of the negative 2. So cotangent of negative x equals negative cotangent x. And your cotangent x is negative 2. So you have negative of negative 2. That is 2. B. If secant x is 0.5, then secant of negative x equals. Secant is an even function. So secant of negative x equals secant x. So I have here secant of negative x equals just secant x, which is 0.5. C. If tangent of x equals 3, then tangent of pi plus x equals what? In this example, I'm not using even odd identities. I'm using the facts that I learned from chapter 5 and 6. That tangent has the period of pi. That means tangent will repeat itself after every pi. So tangent of pi plus x is actually equals to tangent of x, which is equals to 3.